Hello everyone, I welcome you in this lecture on AVL trees. Today we are going to talk about the AVL trees, what are these AVL trees, why we discuss AVL trees, how we do insertions and deletions, all we are going to talk in this lecture. So AVL stands for Adelson, Welsky, Landis. These are the three persons who have proposed the idea of AVL trees. So AVL tree is basically a balanced tree. We always interested to make our tree balanced because it helps us to reduce the cost of the operation. So we will see in the upcoming slide that how we can make the balance of the tree, how we can make the balancing of the tree, and how it is going to help us in reducing the operation cost. Okay, so let's start. So AVL tree is a self-balancing binary search tree. When we talk about self-balancing trees, then we have red black tree is also a self-balancing tree. Now self-balancing assure us that the cost of operation will always be minimal. So here the balancing is done by comparing the height of any node, and then if the height of the node is differing more than one, then we will realize that actually the tree is actually extending to one side. So whenever you find that the difference of the height is going to be more than one, then we need to uh, take some action so that our tree remains balanced. So here you can see in the AVL trees the height of the two child subtrees of any node differ by at most one. So the AVL trees actually assure us that the difference of the left subtree and right subtree in the height will be maximum 1, and whenever you find that the difference is going more than 1, that means the tree is extending to one side, and then we need to do some rebalancing so that it can be balanced. Now here you can see that the given tree is actually balanced, because here now if you look at these values, these represent the balancing factor. So here we will use one term, balancing factor, which basically means the difference in height of left and right subtree. So if the difference is going to be more than 1, then definitely we need to do some work, we need to do some rotations, we need to do some rebalancing so that the tree will remain balanced. Now how to find out this difference? We need to find the difference in the height. Now what is height? Height means the maximum number of edges from the node to the leaf will be the height of that node. So if we say the height of the tree, so here that node will be the root node. So you need to find out the height of the root node, and that gives the height of the tree. So if you look here, so here this is a left subtree, this is a right subtree, and if you want to look to the height of this node, you need to see that how many edges you need to cross to reach to the leaf. So only one edge is required here. So the height of the left subtree is 1, and the height of the right subtree, because there is no child, is 0. So you are getting -1 answer. That means we are doing the height. So balancing factor we are calculating as height of right subtree minus the height of left subtree. This is what we are doing. So here you can see the height of this node will be, this is 0 minus 1, that is, so the height of the right subtree is actually 0 because there is no child, and if you look at the left we have 1, so 0 minus 1 is -1. Similarly, if you look at this, so here the height of this is actually based on the, means if you look at this node, so the height of this node from the left subtree is actually 1 2, and the right subtree is 1. So you can find here that 1 minus 2 is -1. So here you can see this is -1. So here you can find the balancing factor of any node by using this formula. So balancing factor basically tells us the difference between the height of the left subtree and the right subtree. So here you can see that at every point we will see that all are either 0, -1 or +1. So this is said to be a AVL tree. If you look to this tree, now this is not an AVL tree because here the balancing factor at each node is not maintained up to 1. So here if you look to uh, the height of the left and right subtree of 8 and 18, then you will find that it is more than 1. So let us calculate here. So here this is the leaf, so we don't have any left and right child, so definitely this will be 0. So balancing factor is 0 here. But if you look here, we have only left subtree, there is no right subtree, and we are using the formula r minus l, that is the height of the right subtree minus the height of the left subtree, and this will give you the balancing factor. So here the balancing factor is -1, which is okay. If you look here, so here we have 1 and 2, this is again uh, right minus left is -1. Now if you look here, this is 3. Now when I talk about the height, so from this node to the leaf we have two possible paths. You can go by this path, which requires two edges, or you can go by this. But when I say height means the maximum number of edges required to reach to the leaf. So when I say what is the height at this node, then you have to consider this path only. Okay, so if I want to find out what is the balancing factor at this here, so you can see this is actually 3 and this is actually 1. So you can say 1 minus 3, which is -2, which is not maintained up to 1. So whenever you have a value 2, means if you don't have value -1, 0 and +1, that means your tree is not balanced and we need to do some effort to make it balanced. So at this point of time, this is not among any of the three values. That's why this is not an AVL tree. In the AVL trees, every node must have balancing factor either of these values, -1 or 0 or +1. Similarly, if you look here, you can see this is actually 1 and 0. So this is 0 minus 1, which is -1. But if you look here, so this is 1, 2, 3, 4, and this is 2. So 2 minus 4 is -2. So again, this node is also not maintaining the balancing factor of this. So as a whole, this is not a AVL tree, because when I say AVL tree, this balancing factor must be applicable, means balancing factor of value -1 or 0 or +1 must be applicable at all the node. If any of the node is not maintaining these balancing factor values, then the tree is not said to be AVL. Now why we care for AVL trees, why this idea has been proposed, and what is the purpose of studying this. Now whenever you do any operation, so whenever we talk about any data structures, or whenever you talk about any tree, we always concerned about doing operations like searching, finding the maximum, minimum, insertion, deletion. So when we talk about the binary search tree, in the binary search tree we are doing these operations. Now these operations are based on the height of the tree. So the effort which required to perform these operations are based on the height of the tree. And so here we are bringing h means height, and the height of the tree will be defined by the nature of the structure of the tree. Now to understand this concept, let us look to the example here. Let us draw one tree that consists of 7 nodes. Okay, so one tree may be of this type: 1, 2, 3, 4, 5, 6, 7. This is one tree, and we are calling as a skewed tree. Skewed tree is a tree where all the nodes are extended only in one direction. Now I can also make one tree something like this: 3, 4, 5, 6, 7. Now if you look at this tree, the height is 1, 2, 3, 4, 5, 6. So the height of this tree is 6, and the height of this tree is 2. And you can easily observe that with only 7 nodes there is huge difference between the height. and the height will actually tell us the effort required to do any of the operations: search, maximum, minimum, insertion, deletion. So that means we want to keep our height minimum so that the effort required to perform this operation will always be minimum. So how we can keep the height minimum? It will be kept minimum if we are able to make it balance. Balance means whenever you are inserting a node, we are inserting in such a way so that it cannot be skewed, it cannot be extend in one direction, but it will be extending in both the direction. Or you can say in another way that the difference between the two must be 0 or maximum 1, and this is the idea of the AVL tree. So whenever you insert a node, we keep on inserting it and we keep on checking the difference between the height to the of any node for the left subtree and right subtree, and we are allowing the difference up to 1. The moment we find that the difference is going more than 1, that means there is a nature in the tree is observed that it is going to extend in one direction. So we need to fix this, and this needs some effort required, and we are calling and we are doing this effort in terms of rotation. So I hope you have understood that why the balancing of the tree is actually important, because we want to reduce the cost of operation. Now, when the tree gets balanced with n nodes, so if you have a tree with n nodes, then with the balanced trees, the height will be log n. This already we have discussed in our previous discussion, that the height will be the optimal with log n. Okay, so we need to make sure that height remains log n after every insertion, and through this we can guarantee an upper bound. That means if we are keeping our tree balanced, that means we can guarantee that to perform any of these operations, our cost will be big of log n. We always interested to find out the upper bound. That means the worst case. Okay, so let us see that how we can maintain this property. Means what actually is required to make our tree balanced. So one thing to understand, that when you are finding the maximum, when you are finding the minimum, when you are searching anything from the tree, actually you are not going to change the structure. You are simply traversing the tree. You are simply looking in the tree uh, to find your required value. The structure of the tree is going to change only when you are going to apply the insert operation or the delete operation. So we need to understand that how we can do the insertion so that the tree always remain balanced. So we will see that how the insertion can be done. So after every insertion, we must augment the standard BST insert operation. Now, because we are talking about the BST tree, now one thing to keep in mind that AVL is also a BST, binary search tree. Binary search tree is a special tree, is an ordered tree where every node can have maximum 2 child, and it will always maintain the order property. Order property means the left side will be less than the root and the right side will be more than the root. This is called order property. So when we do insertion in the AVL trees, the AVL tree will follow the BST rule. Means whenever you insert the any node, it will always follow using the BST properties. Along with this, we need to augment some more rules to it so that our tree remains balanced. When we talk about the general BST, then your tree is not balanced. For example, if I am going to insert all the values which are in sorted order, for example, if I insert 2, 19, 25, 65, 82, then if you construct your tree, then it will be going like this. Now this is your skewed tree, and the operation will be costly, and this is what we want to avoid. So we want to add something to it into the insertion of the BST so that it will be remain balanced. This is what we are going to understand here. So BST property means that the key at the left side is less than the key at the root, and the key of the root is less than the key of the right. Okay, so here we need to perform some extra task to make it balanced, and we are doing in terms of rotation. So we have two types of rotations. One is called left rotation and other is called right rotation. Okay, now let us look here to understand in a better way. Okay, let us look to this example here. Let us understand that what is these rotations and how these rotations are done. So T1, T2 and T3 are subtrees of the tree. So you can look here, rooted with Y on the left subtree or X on the right side. Okay, so this is one tree is given to us here. This Y is a root and these are the subtrees here. And when you are doing a right rotation at Y, so whenever we do a right rotation at the Y, then what is going to happen? This X is going to become the root and this becomes the right child of this child. So this goes up and Y goes down and this becomes the right child of X, and the right child of X becomes the left child of Y. So you can see here that whenever you apply the right rotation at the Y, then X becomes the root and this Y becomes the right child of X, and the right child of X becomes the left child of Y. So this is what we are doing in the rotation. And when you do left rotation, so if I do the left rotation at X, for example here, then what will happen? Then this is going to become the left child of Y and the left child of Y becomes the right child of X. So this is going to add it here. This becomes the right child of X and X is going to become a left child of Y. So when you do the left rotation, you are actually going to get the previous structure. So when you apply the left rotation, you are going to get this back, this structure. So you can see here. Now one thing important here to note, that whenever we are doing the left rotation and right rotation, the order property is not going to change, and this is the important part, because if the order property will be changed, then the tree will no more BST. We need to do some task keeping in mind that we are working on BST and the BST properties must not violate. The property means the left keys must be left than the root and the root keys must be left than the right. So here you can see, if I do, this is one tree, and if I do the in order traversal, and we are already aware that if you do the in order traversal of any BST, we get the sorted sequence. So if I do the in order traversal here, so it is what we will get, T1 X T2 Y T3. This is in order traversal of this tree. Now again, if I do the in order traversal of this, what you will get? You will get T1 X, then you will go to right, then left, T2, then Y and T3. So what you will observe, this sequence uh, T1X, T2Y, T3, T1X, T2Y, T3 for both the trees same. That means even if you change the structure, this in order sequence will remain the same. So that means our BST property is not going to violate. Now steps to follow for insertion. We already know that whenever you insert a node in the binary search tree, it will always be added as a leaf node, and the insertion will start from the root. So whenever you insert anything, let's say this is your root X, so whenever you insert anything, you need to compare the value with the root. If the new value is less than the X, you need to move to the left side. If the new value is more than the root, you have to move to the right side, and this is how we are doing. And finally, when you get its position, you are going to insert it node. Now let us understand the scenario. Let us, we are interested to insert a node and we are calling it as a W. Now perform the standard BST, that is binary search tree insert operation for W. So this is what we are going to insert. Now here I am using some terminology, like we are using some terms to understand in a better way. So W is our new node that we are interested to insert. Starting from W, traveling up and find the first unbalanced node. Let Z be the first unbalanced node. So after the insertion, so as we have discussed that the AVL tree is also the binary search tree. So first you insert the node in the same way as we are inserting in a binary search tree. But once you have inserted, now this insertion may create a violation in the balancing nature. So because of this insertion, maybe your tree gets unbalanced. Now we have to fix this unbalanced nature. So how to fix this? Starting from W, we need to find out in the tree that on which node we need to perform a rotation. So from W, we will keep on moving upward and we will find the first unbalanced node. So when I say unbalanced node means we are looking for any node whose balancing factor is actually not 0, not -1, not +1. So if you find any node which is not having this balancing factor, that node is said to be unbalanced. Let Z be the first unbalanced node. So we are calling this is the critical node. This is a node whose BF is not among these and it is said to be unbalanced. And Y be the child of Z. So Z is the node which you have find whose balancing factor, let's say +2, and Y is a child of Z, and Y is the node who is actually the child of this node that comes on the path from W to Z. Now W is a node which we have inserted. So let's say you have inserted some W here and you are keep on moving upward, and here you will find that this is a node whose balancing factor is not 0, -1 and +1. So we are calling this as a Z unbalanced node, critical node, and then Y is a child of this node, and X be the grandchild, and X is a child of this Y. So this is a grandchild of Z. So these are the three some notation that you have to keep in mind. Rebalance the tree by performing the appropriate rotations on the subtree rooted with Z. So once we have identified this node, we identified this critical node where the balancing factor is not up to the mark. We have find out who is the child, who is the grandchild, and then we have to do some appropriate rotations and rotations to be done on this node. There can be 4 possible cases that need to be handled, and this will arrange X, Y, Z in the 4 possible ways. So now we need to do some rotations, and we are having 4 kind of rotations possible. First we are calling as a LL case, that is left left case. Left right case is a LR case, then RR case, and right left case. So first you need to identify which type of case is required, and then we will be doing the appropriate rotations. Now what is left left case? Y is a left child of Z and X is a left child of Y. That means this is your Z node and this child Y is a left child and X is also a left child. So means left left. This is called left left case. Left right case means this is your case 1. Left right case means this is your Z. This is Y is a left child of Z, but your X is a right child of Y. So this is called left right case. This is case number 2. Then we have right right case. Right right case is like this, Z, and then you have Y, means Y is a right child of Z, and X is also the right child of Y. So this is right right case. Similarly we have right left case. That means this is case number 3, and case number 4 is we have Z, then we have a right child Y, and then we have a left child X. This is called right left case. This is case number 4. So these are the 4 cases, 1 2 3 4, and first we have to identify that which case is applicable in our scenario, and then accordingly we will do it. Now one thing to keep in mind, that normally when we fall in case 1 or case 3, that is left left case and right right case, usually with one rotation we are able to fix our tree, we are able to make it balance. But when we are having left right case or right left case, we generally have 2 rotations required to make the tree balance. In general, whenever you have left right case or right left case, in the first rotation we are converting to the LL case. So if you have the left right case is actually applicable, then you do one rotation, you actually change to left left case, and then you will do one more rotation to make it balance. Similarly, if you have right left case, when you do a rotation, it moves to right right case, and then again you do one more rotation to make it balance. So in all the cases, we only need to rebalance the subtree rooted with Z. And let's see that how all these cases can be applicable, means how these cases can be identified, and what kind of rotations will be applied to make our tree balance. Okay, so let us understand in a better way that what is left left case. So you can see here, this is your Z, this is left left, and we need to rotate from here. Right rotate Z. So what you will observe, when you right rotate Z, then this becomes the right child of Y. So this becomes the right child of Y, and this becomes the left child of Z. So you can see that this becomes the right child of Y, and T3 becomes the left child of Z, and you can see that this is now balanced, and we did only one uh, one rotation. Now when I say balanced, balance means you can just look at this, that this is actually 1 2 and 1 2. So this is actually 0, this is also 0, this is also 0. So this is said to be balanced. Now left right case. Left right case means this is your left child of Z, and this is the right child of Y. And what is required here, you need to perform the left rotation at Y. So first you will do left rotation here, this is your first step. So when you do left rotation here, what will happen, this will come down, this will move up, and this becomes the left child of X, and this becomes the left child of Y. So you can see here, so when you make a rotation, this comes down, and the left child of X becomes the right child of Y. So this is T2 is the right left child, becomes the right child of Y when you do the rotation. But now you can observe here, this has actually shifted to almost left left case. We have Z, X and Y, though now the position of Y is moved here down and it moves up, but the scenario is this is a left child of this, and this is a left child of again this X node, and our tree is still not balanced. Now you can see here, this is only 1, this is 1 2 3. So this is, if you do 1 minus 3, you will get minus 2, which is still unbalanced. So what is required, you need to do one more rotation, and now you will be doing, you are actually almost the LL case, and you have to do the right rotation here. So when you do right rotation here, what you will find, this node goes to down, the right child of this node becomes the left child of this node. So you can see here, Z goes down and the right child of X becomes the left child of this, and now this is balanced. You can just find out the balancing factor at each node, and you will find that this is 0 or maybe 1 in some cases, but not 2. Then we have right case. So this is right child of Z, this is X is the right child of Y. So again, when we do, this is just a mirror case of the left case. In the left case, we did a right rotation at the Z, but here we will do the left rotation at the Z. So whatever we did in the previous case, now we are doing the same thing, but in the reverse direction. So again, now here we are doing to make a left rotation. So that with the left rotation, what will happen, this will go up, and this becomes the child of this, and the left child of this become the right child of this. So here you can see this Z goes down, and the left child of Y become the right child of Z, and our tree is balanced. So just keep a note that when you do LL case and RR case, only one rotation is sufficient to make your tree balance. But when we do the right left case or the left right case, we have seen that two rotations are required in LR case. Similarly, you can find that with the right left case, the same thing is happening, because this represents the mirror image or the mirror case of the LR case. So here, this is your right child and this is left child. So right left case. So first you have to do the right rotation at y. Previously we did the left rotation here, but now because this is a mirror case we have to do in the opposite direction. So you do the right rotation here, and with the right rotation you get this figure, this structure you will get. But again you will realize that this is not yet balanced, so we need to do one more operation. With this right rotate you actually get the right case. So you have to again rotate from the root, that is z, left rotate, and you will get this structure. So this is how we are going to do the all these rotations by identifying the cases. So this is a summary. You can see here all the four cases are visible to us now. So you can see in the left case and the right case only one rotation is required. So here we are doing the right rotation. So whenever the case is left, you are doing the right rotation. Whenever the case is right, you do the left rotation. Whenever you are having a left right, so first you do the left rotation and then you do the right rotation. When you have the right left, so first you do the right rotation and then you do the left rotation. So this is how you can just memorize that what kind of rotation is required whenever you got stuck in this kind of unbalancing nature of the tree. Okay, so let's move to the next. Now this is one example to realize that how these operations can be applied, or you can say how these rotations can be applied on any tree to make our tree balanced all the time. Now this is one scenario. This is one subtree you can say, and the structure says that this is something extending, there is not extending. So the BF, the balancing factor of this node is -2. That suggests this is not a AVL tree. So let us take one example here. This is one tree. This is a binary search tree, but this is not AVL. Let me check here. This is AVL. This is AVL because all the nodes are having the balancing factor less than 2. Okay, or you can say they have -1, 1 and 0. Okay, now on this tree we are inserting a node value 3. So how to insert a node value 3? We have to start from the root. So we check 3 is less than this, we go this side. 3 is less than this, we go this side. 3 is less than this, we go this side. 3 is less than this, we go this side. Now after inserting a node, every time we need to check the impact of balancing factor on this insertion. So when you find out, we will find this is actually -1 because this is 0, this height is 0. So 0 minus 1 is -1. When you do here, so 1 minus 2 is -1. When you do here, so this is 3 and this is 1. So 1 minus 3 is -2. So keep in mind how to do rotations. We have discussed that you have to first insert the node. We have inserted the node, and then you have to move upward to check which node is unbalanced. So we move upward here and we find this is unbalanced, and then we will find the y which is the child of this and find the x which is the child of this in the same root where you have inserted, because this is also the child of this node, but we will be taking this as x because we have to move into the path which actually gives you the node which you have inserted. So this is y here, this is x here, and you can find this is the left child of this node, this is the left child of this node, and this is a L case. And in the L case, what you have required, you do the right rotation at the root. So root means this means at the critical node. This is the node that actually is unbalanced. So you have to do the right rotation here. So when you do the right rotation here, what will observe? This goes down, 5 goes up, and this becomes the right child of 5, and the right child of this becomes the left child of 10. So you can see here, this goes up, 10 goes down, and the right child of 5 becomes the left child of 10. And here you can see that what is the impact of this rotation. You can now again find out the balancing factor for the entire tree, and now it is all -1, 0 or +1, which is actually balanced. So now we are able to convert into the balancing trees. Let us take one more example. This is one example where again the tree is not balanced. So let us take this tree. So initially we are having a tree which is a AVL tree because it's a binary search tree, and also the the structure is balanced, means the balancing factor at each node is maintained, means 0 plus 1 and minus 1. Now we insert 45. So when you insert 45, how we start? We have to start from the root. 45 is more than 30, we go here. 45 is more than 35, we go here. 45 is more than 40, we go here, and we insert this node here. So we insert a node in the normal process like we are doing in the BST, but because of this insertion, there is a possibility that the balancing factor of these nodes may get disturbed. So we have to check it again. So this is plus 1 because we have to do 1 minus 0. Now here this is 2, 2 and minus 1, which is plus 1. Now you can do here, this is 1, 2, 3. So 3 minus 1, which is 2. Now this is not balanced. So we have to find out the case and then we have to do the rotation. So let us find out the case. So this will be your Z, this is your W, this is your uh, Y, and this is your X. So here you can see the case is right, right. That means you need to do the left rotation here. So when you do the left rotation here, what is going to happen? This becomes the left child of 35 and 32 becomes the right child of 30. So you can see here, and because this is right rotation, only one rotation will make it balance. So we have seen the case of left, right. Now let us move to take more example to look into the different scenario. Okay, as you see, this is again AVL tree because we are maintaining the rule property, that is means the left side is less than the root, right side is more than the root, and also the balancing factor is also maintaining the balancing values like plus 1, minus 1 and 0. You insert the 15. So after inserting, now I am assuming that already we are now comfortable in inserting a node. So 15 is inserted here, this is 16, this is 15. Now once you insert the node like a BST tree, then we have to calculate the balancing factor. So we will calculate and we will find that this is plus 2, and I believe that you understood how to calculate. So here you can see this is the height is 2, the height here is 0, so 2 minus 0 is 2. Now this becomes your Z, and this becomes your Y, and this becomes your X. This is also your W. Okay, now this is the case of right, left. This is right child of Z and this is left child of Y. So RL case. So first, when RL case is there, you need to do the right rotation at this node. So we have to do two rotations. One is the right rotation and the left rotation. Right rotation we are doing to the immediate node, means to the child of the main critical node, and the left rotation we are doing at the critical node. This is what we have seen so far. Okay, so when you do the right rotation here, what you will get, you will get that this is going to down and 15 will come here. So this is what you observe. So this is your 15 will go here, 16 will go down, and actually you have moved to right case. In this case you have to actually again do a rotation. So you have to rotate from here, and when you rotate from here, 15 will go up and 9 will go down. So you can see this is how this situation will come, and if you calculate the balancing factor of each node, and you will find this is balanced. So with two rotations we are able to fix our problem. So we have seen LL case, RR case, RL case, and now similarly we can also do the left right case. The left right case is again the very similar. So when we get left right case, you have to do the left rotation first at the Y node, and then you have to do the right rotation at the Z node, and you will able to get your AVL tree. I feel you have understood all these rotations. In the next video, in the next part of this lecture, we will be discussing about the deletion, that how the deletion is to be performed in the AVL tree. So this is all for the insertion. Thank you very much. Take care.